Okay, calculus, we're on day 5 of Unit 2, and we're going to show you some new rules for derivatives today. So I'm going to differentiate or find the derivative of these three functions, and we're going to do it in two different ways. They're both perfectly acceptable. So the first one, f at x equals x squared plus 2 times x plus 5. Let's just rewrite that. Okay. F at x equals x squared plus 2 x plus 5. The old way, which is perfectly acceptable, is to expand and use our rules of derivatives. Okay, so if I expand that, f at x is, I'm just foiling, is x cubed plus 5x squared plus 2x plus 10. Now I'm comfortable using the rules of derivatives that we used the other day, and I bring down the power and reduce the exponent by 1. Bring down the exponent, reduce it by 1, and 2x just becomes 2, and the derivative of 10 is 0. So I have my derivative, perfectly acceptable way to do it. But there is another way to do it. If I have the function x squared plus 2 times x plus 5, I have what we call the product rule. We're going to summarize it a little bit later, but the product rule would be if I have a product of two different functions, I'm going to call this one g of x and this one h of x just to separate them and make them clear. Then my derivative can be written as the derivative of the first guy times the second one plus the first guy times the derivative of the second. So let's try it. See if I'm telling you the truth. Looking back at my original function, g of x is x squared plus 2. So the derivative of that thing is 2x, because that 2 becomes a 0. I'm supposed to multiply that by the h of x exactly the way it is, plus. Now I write my first function the way that it was, x squared plus 2, and I take the derivative of the second function, and the derivative of x plus 5 is just 1. Let's expand that. 2x times x is 2x squared. 2x times 5 is 10x. Then the second 2, oh, that doesn't change anything, x squared plus 2. Final answer would be 3x squared plus 10x plus 2. Very same answer as we had doing it the old way. Didn't look a lot easier at this point, but this wasn't a terribly bad function. Let's do the second one. The second one was, oops, sorry, b. F at x, let's do y equals x squared minus 3x, x 5 plus 2. So the old way is to take my function first and expand it, and then use the rule, the derivative rule. So foiling, I have x to the 7 plus 2x squared, subtract 3x to the 6th minus 6x. The derivative of that I could write as y prime or dy dx. My derivative would be 7x6. Brought the exponent down, reduced it by 1, plus 4x to the 1, subtract 18x to the 5, subtract 6x to the invisible 0. Nothing I can do with that. Or I can think of that as y equals x squared subtract 3x. It's my first function times x to the 5 plus 2 is my second function, which I'm multiplying, And my derivative, y prime or dy dx, would be the derivative of the first times the second plus the first derivative of the second. Okay. The derivative of the first would be 2x squared minus 3x. So 2x subtract 3 times the second exactly the way it is, x5 plus 2. Pause. I want the first function exactly the way it was, x squared subtract 3x times the derivative of the second, which is 5x to the 4. I'm going to tidy those up by doing FOIL on the first two, 2x to the 6 plus 4x, subtract 3x to the 5, subtract 6. I'm going to do distributive law on the second two. I have 5x to the 6, subtract 15x to the 5. Put those together, I have 7x to the 6. Okay, I have, so that's my x6s, my x5s would be negative 18 of them. I have x's and I have numbers. There you go. The same. So expanding first and doing your derivatives piece by piece is fine, or using the product rule. One more. I keep showing you. Okay, C. Y equals x squared plus 3x plus 5 squared. Okay, so we can do this one the old way, which is to expand this function first and then take the derivative piece by piece. So what this means is x squared plus 3x plus 5 times x squared plus 3x plus 5. So we've got the FOIL or distributive law gone bonkers, however you want to think of it. I've got x squared times all three terms would be x to the 4th plus 3x cubed plus 5x squared. Okay, he's done. Plus 3x cubed plus 9x squared plus 15x. Okay, he's done. Last, 5x squared plus 15x plus 25. Done. I would tidy that up before I found the derivative myself. I have x to the 4th. Cubes, I have two piles of those, so I have 6x cubed. My x squareds, I have 5, 10, 19. My x's, I have 30x and 25. So if I want to find the derivative of this thing, I have expanded it, and I can use that power rule, bring down the exponent, reduce it by 1, 18x squared plus 38x plus 30, and the derivative of 25 is 0, so we have our derivative. The new way is to use what we call the power rule. We're going to summarize that in a moment, but if I have the function y equals x squared plus 3x plus 5 squared, I can write my derivative as, okay, I have this thing raised to the power of 2. So derivatives are bring down the exponent, reduce it by 1. So I bring down the 2, put everything in that bracket the way it was, reduce that exponent by 1, but I don't have a simple x to the power of 2. I have ugly to the power of 2. So I bring that power down, reduce it by 1, and don't forget the derivative of the ugly. We call that the power rule. So we take the derivative of the function itself and then take the derivative of the guts. There. If I were to expand that, I would have what I have written in blue. I bet you anything. Okay, so I'm going to deal with the 2 first. 2x squared plus 6x plus 10 times 2x plus 3. I'm going to deal with this guy first. I would get 4x cubed plus 12x squared plus 20x. Pause, plus, deal with him now. 6x squared plus 18x plus 30. Tidy that up. 4x cubed. I have 2 piles of x squareds. I have 18 of them. Plus 38x plus 30. What do you know? The answer is the same. So we've introduced 2 tools today that can be very helpful, but you can always do it the old way by expanding. So here's our product rule, which we've already written out for you. If you have a function that looks like a product, then your derivative can be found by derivative of the first times the second plus the first derivative of the second. This one we haven't written out yet, the power of a function. So you've got something ugly in the brackets to the power of n. We bring the n down and reduce it by 1 like we always have, but don't forget to take the derivative of the guts. Okay, we're going to do a couple more, and we're going to use the rules the way they are. Okay, f at x equals x squared plus 2 times, oh, sorry, those are the ones we just did, onwards and upwards. 5x plus 1 cubed times x minus 4. I like this example, and not just because I made it up, but because it has a power rule and a product in it. And I could probably convince you that expanding that thing for a half an hour might not be worth your time. So what I see is a function that is g of x times h of x. So it has 2 pieces to it. And if I want the derivative, I need to take the derivative of the first times the second plus the first derivative of the second. So I'm going to write that out. Derivative of the first times the second, whoops, don't need brackets, plus the first derivative of the second. Just that the derivative of the first is going to be a little bit complicated because it's a power rule. Here we go. The derivative of the first. I have the derivative of 5x plus 1 cubed. So my derivative would be bring down the 3, make that exponent a 2. And I'm going to write the inside exactly the way that it was. But don't forget, for the derivative of this power rule, I need the guts. So the derivative of 5x plus 1 is 5. Guts. Okay. Times the second, exactly the way it is. If I could write, we'd be fine. All right. Now I have the second half of the product rule. I have to write the first one exactly the way it was. Plus 5x plus 1 cubed. And then I need the derivative of the second. And the second is x minus 4. The derivative of x minus 4 is 1. I'm going to write it down just so you know that I thought about it. Okay. I just have to tidy this thing up. A little bit messy, but doable. And a word to the wise, to tidy this thing up, the best way to write it is in factored form. So bear with me here. My tidying is going to leave it in factored form. And as I look across this thing, I see the factor of 5x plus 1 is common to both sides. So for the first mess, I see 5x plus 1 squared. And for the second term, I've got 5x plus 1 cubed. So 5x plus 1 squared is the common term, common factor. Okay. For the blue pile, I have 3 times that, times 5, times x minus 4. So I have 15x minus 4. For the black, the second half, I have 5x plus 1 cubed, and I've already factored out 5x plus 1 squared, so I'm going to put 5x plus 1. This is really helpful for later on when we go to look for graphing things or looking for x-intercepts or zeros and whatnot. Leaving it in factored form is best form. Okay, I'm just going to tidy that bracket up a little bit because it is a little bit hideous. I've got 15x subtract 60 plus 5x plus 1. So I have 20x. Subtract 60 plus 1 is subtract 59. There, best answer. Let's try the second one. F at x equals 3x squared plus 4 times 3 plus x cubed to the power of 5. Here we go. We have both product and power rules involved in this thing as well. I see one function and I see a second function that is itself a power, so we'll have to be careful when we take the derivative. Okay, so my derivative is f prime at x. I'm going to write the rule out again. It's the derivative of the first times the second plus the first derivative of the second. The derivative of the first is not a power rule, so I just look at it, 3x squared plus 4, and its derivative is 6x to the 1, and the derivative of 4 is 0. Yay. I write that multiplied by the second function exactly the way it is. 3 plus x cubed to the 5 plus. So I have done that and that. For the second half, I have the first exactly the way it is, 3x squared plus 4. And now I need the derivative of the second, and it's a little bit on the ugly side. So the derivative of the second is bring down the exponent, reduce it by 1. Don't forget the guts. The derivative of the inside of that bracket, derivative of 3 is 0. The derivative of x cubed is 3x squared. Please forgive my wraparound. So this whole thing is the derivative of h at x. And this little piece right here is the guts. Don't forget the guts. I'm going to tidy this up. I am looking for common factors to just make it neater. I see that I have 6x. I see that I have an x in both piles. I have an x here, and I have an x here, so x is going to be part of my greatest common factor. I have 3 plus x cubed in both piles, and I have to have a greatest common factor of 3 plus x cubed to the 4. Okay. For the first term, I'm missing that 6, and I'm missing one more 3 plus x cubed. For the second pile, I have a 5 missing. I have 3x squared plus 4. I've already taken care of the 3 plus x cubed to the 4th. I'm missing a 3 and another x. So I'm going to change this to 15x. All right, just checking that I didn't miss anything. So my greatest common factor, x, 3 plus x cubed to the 4th, and then this big bracket, if I can tidy it, that would be awesome. I have 18 plus 6x cubed plus 45x cubed plus 60x. With my luck, I've made a boo-boo, and I'll have to backtrack, equals x. 3 plus x cubed to the 4th. I have 51x cubed plus 60x plus 18. Best answer. Not best answer. I did not notice that there is a factor of 3 in that square bracket, so I missed it earlier on. But that's okay. I can take it out now. So I've got a factor of 3 in the square bracket, so I'm going to take it out. I have 17x cubed plus 20x plus 6. Okay, so learned 2 new rules and reminded you about factoring. It's a good day. Last one for today. Let's do C, red for danger. F at x equals 1 minus x squared to the 4th times 2x plus 6 cubed. Would not want to do this the old way. With all that expanding, you'd be here till Monday. Let's do our rule. So we have one function, which is a power, and a second function, which is also a power. So our derivative is going to be interesting. Okay, the derivative of the first times the second plus the first derivative of the second. Okay, the derivative of the first. Bring down the 4. Reduce the power, or the exponent, sorry, by 1. Don't forget guts. Times the second, exactly the way it is. Okay, that's the first half done. Plus, I'm going to go on to the second line. The first times the derivative of the second. The derivative of the second is bring down the exponent, reduce the exponent by 1. Don't forget the guts. I'm just going to remind you not to forget the guts, because that is a sticking point. That was kind of a gross metaphor there. Okay, don't forget the guts. Now we're going to tidy it up, our very favorite part. We are looking for a greatest common factor. So for the 2 piles, I am looking for numbers. I have a 4 and a negative 2. The second I have a 3 and a 2, so 2. I have an x where I've underlined guts in the first one, but no free roaming x's in the second. I see brackets with 1 minus x squared. So I go with the smallest power of that, which is 3. I have some 2x plus 6's in both piles. I go with the smallest power, which is that. Okay, now I square bracket. For my first term, I have a 2 out there, but I am missing a negative and a 4 and an x. I already have the 1 minus x squareds taken care of. I have 2 of the 2x plus 6's, but I need a third one. Okay, that's the first half. Second half, I need a 3. I have 3 of the 4 1 minus x squareds, so I need one more. I have the 2x plus 6's taken care of. I'm done. Okay, almost. I have square bracket that just could use a little tidy up. Okay, here we go. I have negative 8 x squared, negative 24x, plus 3, subtract 3x squared, 2, 1 minus x squared cubed. And what can I put together in here? I have negative 11x squared, negative 24x, plus 3. Final answer.